As you all know, electrodynamics is one of my favorite sections. So we're going to start by going from scratch basically and looking at a magnet. You all hopefully saw this in class. When we have a normal magnet, bar magnet, when we put the iron filings on top of the bar magnet with the paper like we did, you can see the patterns forming, but you obviously don't see the arrows. So the direction is defined from north to south, so the red one here is north. The lines then go around from north to south, and you must also be able to draw it between two different poles, a north pole and a south pole, where they would just go directly, and two opposite poles. So here it would be going away from this north pole, but also away from that north pole. If these were two south poles, it would be going towards the one south pole and towards the other south pole. So just make sure you can draw the field lines around a bar magnet. But that's just one magnet, and we now have to look at electrodynamics. So we're going to look at how electricity affects how magnetism and electricity can basically work together. So the first thing we're going to look at is just if I have a wire, just a straight wire with a current flowing in it. Now on a piece of paper, it's difficult to show a straight wire. You can see it at the bottom, and I'll bring those up now. But we use a cross to show something coming out of into the page, away from you. So that would be like throwing a dart, and the dart is moving away from you, which means you see those little feathers at the back of the dart. Or we can use a dot, which means it's coming out of the page. Remember, you are answering this on a piece of paper. So please be clear what direction you are talking about. So this is out of the page towards you. So you can basically lift the page up like the screen is in front of you. And if the current is flowing, remember the symbol for current is I. So if there's current flowing in the conductor, then you will see, and I hope you did this in class, when we place little compasses around this wire, the compasses all align in a specific direction, and they will form a circle around these wires that now have current flowing in them. And the direction in which the magnetic field would be then can be predicted using the right-hand rule. You can obviously do it with compasses every time, but you can use your first right-hand rule to predict this. And the way we do it would then be as shown here. So you can see here, your thumb points in the direction of the current. Remember, we use positive to negative as the direction of conventional current. When it's electron flow, it will be in the opposite direction, but we generally work with conventional current. So from positive to negative. So if I was drawing on this one, it would mean that this is positive, and this side here, where my picture doesn't want me to right now, is going to be negative. Now you can see the thumb points in the direction of the current, and then your curled fingers show you the direction of the magnetic field around that wire. So that diagram kind of shows it nicely, and you can see it there in 3 dimensions. But remember, you're still going to answer this on a piece of paper. So to help with that, we're going to use the symbols that you've seen at the top there. So into the page, out of the page. So for this one, if you take your finger and you basically point it out of the page, and you hold your thumb on the screen with your thumb pointing away from you, or if it's your exam paper, your thumb pointing, towards your face, because this one's coming towards you. And you will see that the magnetic field lines will be going like that, which is anti-clockwise. If we look at the one at the bottom, on the right, left, so here it's going away from you into the page. So into the page, point your thumb into the page, and you will see that your magnetic field will be going in this direction. So that will be clockwise. So be clear. If it's a circle, answer clockwise or anti-clockwise. Don't try and use fancy words for this. Now that's one little wire. We don't always look at just straight wires. Just one thing I need to mention. The stronger this current is, the stronger that magnetic field is. And the way we show that on a piece of paper, the magnetic field or magnetic flux density, we'll get to the terminology again later, but magnetic field strength, like for electrostatics and any other field, is shown by the density of the line. So when these lines, if this one had a stronger current than this one, then the lines will be denser. So not necessarily just more lines, they must be denser. So in the same space, there must then be more lines. And make sure that your lines do not cross. Try and draw them as neatly as possible, not as wonky as mine here. Alright, so that's for a straight conductor. Now, often we don't work with straight conductors and we work with coils or solenoids. Now, what that is just your wire turning in a loop, like this little diagram here at the bottom shows you. So I'm just going to bring that one up. So now if we look at this one, I actually want you to see it differently. So here we're going away from us into the page, and at the bottom it's coming towards us. So if I was going to draw that on a piece of paper again, these top lines, so if it was just one loop, then it would just be one cross at the top, one dot at the bottom, because it's coming towards us here at the bottom. So we'll have a magnetic field there around each of them. I'm just going to draw one circle. You can obviously draw more. Now this one again is going into the page away from us. So the magnetic field is going around that way, clockwise. The bottom one is coming out of the page towards you, and the magnetic field is going anti-clockwise like that. Now this is just one loop. So if one single loop, but if I now go and add these dots for every single one of these lines that you see here, it means all the ones at the top will be going away from me. This is talking about the current. Remember, the current is going away from me because here you will see the current flows from positive around, and towards negative. We use conventional current. Now each of these will do exactly the same as that first one. So you will see these little circles, or you can draw those little circles, you don't necessarily will see them, and each of them will look like the first one. So you'll have clockwise magnetic fields around the top ones, and you'll have anti-clockwise magnetic fields around the bottom ones. Now if you look at the combined effect of all those little circles that we've just drawn, you can see here it's all going this way. If I was drawing lots of circles, this way, and this way, and this way. And I can even carry on, but I'm hoping that you are seeing a resemblance between what I've just done and what you've had here before. A normal bar magnet here had a similar magnetic field structure. So what we actually did is we made a magnet. So a solenoid with a current flowing in it is creating a magnet that is caused by electricity, and therefore we call it an electromagnet. Now you can increase the strength of this electromagnet by increasing the current, because remember then the lines will be more dense. You can also increase the strength of this electromagnet by adding more of these windings, because each of them form a field around it. And then you can also increase the field around that magnet by taking a soft magnetic material. Now just again, that means that the magnetic material gets magnetized quickly and loses its magnetism quickly. So as it's in this magnetic field, this soft magnetic material will also become the same as what we have for the electromagnet. It will get magnetized as well. So we get extra field lines. You can use the pink and the green. So the pink and the green lines together forms a more dense field, and therefore I have a stronger electromagnet. So there's three ways then in which I could increase the strength of this electromagnet. Now you can go and draw these circles every time you get a solenoid, but we can also use our right-hand rule again just a little bit differently to determine the polarity of this electromagnet. Now, please don't confuse it with the direction of the magnetic field. The direction of magnetic field is always from north to south. When we use our right-hand rule to determine the polarity of a solenoid or an electromagnet, you will use your right hand again. This time, the cooled fingers shows you your current. So you can see it comes around and you can basically hold the solenoid like this diagram is showing. And your fingers will show the direction of the current. So it will go over like the current did. And then your thumb points in the direction of the North Pole. Not north to south. It shows you where the North Pole is. It's a shortcut to show you the direction of to show you the magnet that you have created. If we look at this magnetic field here in the middle, just remember in the middle here, the field is going this way, and on the outside, the field is going that way, but it looks exactly like a normal magnet, and you'll see away from this side. So now we can use our normal convention from north, because it's going away from north towards the south. So these two things are actually exactly the same. Now moving on, we're going to look at when a force is now actually created, because we need to get to dynamics. We're on the electro part already, but we need to get to how this is causing motion. So I'm going to just quickly do it using two conductors. Because if you understand this principle, you will understand it for everything else. So if I have a conductor that a current flows in and another conductor that a current flows in, and I switch on these currents, so therefore I have magnetic fields forming around. Now for this one, it's going into the page again. You must please each time lift up your hands and do this with me. It's going into the page, the current, so the magnetic field is going to be around clockwise for both of them. Now, if we keep on doing this, and this one, as you go further, yes, it will get weaker, and this one, as it goes further, yes, it will get weaker. But what you will see here, where the two magnetic fields interact with each other, and this is the whole basis of electrodynamics, basically. Here in the middle, you can see that it's clockwise, and here it's clockwise. But if you look at the field here, the two fields are going in opposite directions, so they will basically cancel out each other. So in the middle here, you will have a low magnetic field density. Now I'm always going to use B when I refer to magnetic field density. So you'll have a low magnetic field density, and on the side you're still left with the same magnetic flux density that you had. So if there's a lower density, you know already, it's almost like creating a vacuum when you're looking at air particles. And when you do biology, it's always from a high density to a low density. But what's going to happen is these wires are going to try and fix what I've done. So it's going to move these lines inward. So that means this wire is actually going to experience a force towards the middle. And this wire will also experience a force towards the middle. So because the two fields are going in opposite directions, these two wires will be attracting each other. This one will experience a force and this one will experience a force. But remember, the force is between the two wires. So the force experienced by this wire will be exactly the same as the force experienced by this wire, even if they have different strength of currents, because of Newton's third law that says if wire A exerts a force on wire B exerts that same force on wire A. And you should remember that force is always between two objects. Now this is the start, because that still doesn't help us much, because we don't want two wires now being attracted to each other. It's not really going to form any useful apparatus for us. So this leads us now to the motor effect. If I have a permanent magnet, so that means, now remember, this is part of a horseshoe magnet or a big magnet. You can't just have a North Pole and a South Pole. So this is part of something. So there's my North Pole and there's my South Pole. And because I have this area in between, I'm going to create a uniform field. That just means that for the bit between this North Pole and the South Pole, the lines are going to be evenly spread. So I could use my nice straight lines, and I can say there's an, oops, not so straight, there's a magnetic field created between this North Pole and South Pole. And you should know by now that the direction of that magnetic field will be from north to south. So the permanent magnet has a magnetic field existing already. Now I'm going to switch on a current inside that magnetic field. So let me just use another color there. So I'm going to place a wire in this magnetic field, and let's just say the current is going now. Remember, current is I. Current is going away from us into the page again. Now I can draw the circles as we've been doing around this wire. Again, it's going to be clockwise, because if you use your thumb into the page, it's going to be clockwise. And now you need to see the same thing. Can you see here that the two magnetic fields are interacting with each other? There's now a blue magnetic field line as well as a green magnetic field line. So I form a stronger or a more dense magnetic field. At the bottom, the blue lines are going this way and the green lines are going this way. So these lines here are going in opposite directions, which means they cancel each other and I form a low density magnetic field, or a weaker magnetic field. Now again, what's going to happen to this little wire is going to try to solve this problem by evening out the field. So this wire is actually going to experience a force downward. Again, you can see from a high density towards a lower density. So the wire will experience a force. And now I have dynamics, because now this wire is going to physically move down. And I have something moving. As soon as I switch on the current, and hopefully some of you have seen the kicking wire, as soon as I switch on the current, the wire will experience a downward force and you can see it moving. Now this is super important, and before I move on to how this is used in a motor, I just want you to just do a quick question that they sometimes ask in papers. So if I have that wire like that, they sometimes put this on, and hopefully you've come across questions like this. They put this all on a scale. And they say the reading on the scale is 20 grams. Now you need to think for yourself, what is actually on the scale? It's just the two magnets. It's the North Pole and the South Pole that's causing the 20 grams. And remember, that's weight. That's the weight of the magnets downwards. Or it's the mass, but it causes the weight of the magnets downwards. So it will be you can convert that. It's not important right now. So what now is going to happen, because the magnets are here. Now the question often says there's a rigid wire placed in this magnetic field. What they mean is that this wire then cannot move. It is stuck in position. And we've just determined that that wire will experience a downward force. Now remember, if the wire experiences a force because of the magnets must also experience a force because of the wire, because these two magnetic fields are interacting with each other. So if the wire experiences a downward force, then you need to realize that the magnets will experience an upward force. So which is the same size as this pink force, because it's Newton's third law. Force of magnets on wire equals force of wire on magnets. So the wire will actually, when you switch on the current in the wire, the two magnetic fields interacting will cause the magnets to move up. And because the wire is not touching the scale, this reading will not be 20 anymore, because the magnets are being lifted up a little. The reading on the scale will drop. Very important. Now, if I look at the diagram at the right here, it's basically just showing you the combination of what I've drawn earlier. So just to have, for you to have a clear picture, I just included that. So you can see if the field is going in the same direction, then it's going to reinforce each other. If the field is going in opposite directions, then it's going to cancel each other, and hopefully you can go and do this again using the low density here and see that the wire will experience a downward force. Now they can ask you how we can increase the force acting on this wire, and you have an equation for this in the SAGS document that I haven't really referred to, but you know all of these are based on the SAGS, so you will see them always here somewhere on the side. So here you will see that you get an equation F equals BIL sine theta. Now if you look at that equation, F equals BIL sine theta. The sine theta basically tells us that the maximum force will be experienced when the angle between the magnetic field and the current is 90 degrees. If it's anything smaller, the force will be smaller. So we need to try and make this sine of 90 because then it will be 1 and that's the maximum value it could be. That's the one thing. So you can keep the wire at a 90-degree angle to the magnetic field to make sure the force is the maximum. You can increase the length of the wire that is actually in the magnetic field. You can increase the strength of the current in that wire, and you can increase the strength of the magnetic field. Now remember, if you're saying increase the magnetic strength of the magnetic field, you didn't give a practical way. So you must say use a stronger magnet to increase B, the strength of the magnetic field. And all of those things will then increase the force or decrease the force, whatever one they ask you. So as these increase or decrease, this will increase or decrease because they are directly proportional to each other. Now we can look at the motor. If you look, you need to do the hand rules. So you're not going to, you're welcome to always go and draw these lines and you will always get the right answer by doing it. But again, there are hand rules to make our lives easier. Now I've put all of it here. You are all familiar with Fleming's left-hand motor rule. Now this is Fleming's left-hand motor rule. I call it the FBI rule because you hold your fingers as if you would shoot something. F is then your thumb, which is your force. This is actually the motion of in which direction the motion will be. Your index finger here is the magnetic field and your middle finger would be the current. Now if you go and you use that for this wire that we had here, and you say I is going into the page, so you push your middle finger literally into the screen. Your index finger points from north to south, so that would mean towards the right. Then you will see that your thumb points down and it shows the F that we already determined. So it just confirms what we already had. This is just showing it again. If you get confused with this, I like what I call the slap rule. It's called the right-hand vector rule. It allows you to use your right hand for every single one of these laws. And you can then, I'm just going to make it a little bit bigger again here. So what you can do is you can use your hand, your right hand, your palm will always face south. So I say you have to slap south. Your fingers, the will always give you the input and it forces you to think about the energy conversion. So the input will be the current, which means it's electrical energy, and your thumb will be the output, which is the force in this case, but it's the motion, it's kinetic energy or mechanical energy. So it gives you that mark already for the energy conversion that is always asked or often asked. Now, if you take this again to this question, to this example here, you must go and practice this a lot. I don't have time to do many examples here. So if you use it here, the input is current. So you face your fingers into the page. Your you have to slap south, so your palm slaps towards the right-hand side, and then you'll see that your thumb, which is the output, is going to be down. Again, it shows you the energy conversion. So energy conversion is going to be, for a motor, it's going to be electrical energy into mechanical energy. Please take note of that. This is a summary of how the slap rule works. And you need to remember, for motor, the input is the current and the output is the force or the movement. Now, how is this used in a motor? In a motor, we have the one side, the current flows in that direction because it's going from positive to negative. We call it a DC motor because it has a DC power supply. A motor is named according to the input. So positive to negative, and you can see here the current goes that way. Now I want you to use your slap rule and determine the direction, or your any rule you want. You can use your left-hand rule as well. And you would see that this side is being pushed upwards. This side, the current is flowing in this direction, so it's being pushed downwards. So it gives us a nice rotation. But then if this little appliance or piece wasn't here, when it gets to this side, the current would still be flowing up into that direction. So that means this would still be pushed up. So what you will have is it will go this way, then this way, then this way, then this way. And that is not very nice for a motor. We don't want that in a motor. So that is why this piece of appliance here is super important. It's called a split ring commutator. Now, the split ring commutator allows the current to change direction every 180 degrees. So when it gets to this side, you will see the current is now connected to the negative, so it flows in the opposite direction, and therefore will now not be pushed up, but be pushed down again. So the commutator allows for the motor to be rotating in one direction only, instead of going up, down, and that we don't want. Now we could look at a few past paper questions, but I have given you all this, so you can go and look at these questions and now see if you can answer all these questions on motors.